today we will start the electromagnetic induction. That is, in short, it is known as the EMI, electromagnetic induction. So first part is basically to deal with some kind of experiment. So from this experiment, you will learn that why this chapter is essential, why you are looking for this particular chapter, what is the benefit of this chapter, or what you are going to learn from this chapter. Okay. So initially, before the start of this chapter, so different scientists do some kind of experiment. Okay, based on those experiments, like the Wested. So Wested also performed the experiment. So from Wested experiment, what we learn about the magnetic force and magnetic field. Similarly, some experiments have been carried away, so which will give the feeling that this particular chapter is much more effective. Why? In terms of production of electricity. So with this particular chapter, we are going to produce some kind of electricity. Okay. Now, what is the essence of this chapter? So, if electricity is moving in a wire produces magnetism. Okay, so this is the first topic that we have learned, that is called the magnetism chapter. In magnetism, what we learned that whenever there is a current carrying wire is there, some kind of current is being flowing. Let us say I amount of current is being flowing through this wire. So, because this wire, some kind of magnetic field is being produced at a distance from the wire. Okay, so if electricity in a moving wire produces magnetism, then opposite is also true. So scientists are thinking this way that if I can produce B, if I can produce B, which means current is going to produce the magnetic effect, that is the magnetic field. So why not the opposite one? Why not the opposite one means the magnetic field can also produce the current. Okay, so opposite one is the magnetic field can produce the current. So a magnet moving near a wire could produce the electricity. So if I allow the current to flow through this wire, so you observe that there is a magnetic field that is being produced. B effect is being produced through current carrying wire. That is true. That is why established that whenever if I supply the current through current carrying coil or where the current is being produced or the magnetic field is being produced. So reverse is also true. If I move a magnet, through this coil, so this coil is initially no. So whenever I am saying the current is being supplied, that means through the wire, if I want to supply the current, that means I have to supply it with battery. Okay, so battery is connected, so that battery will, once you switch on the circuit, now the current will. But what you look in the second experiment that if I move the magnet inside a coil, so then the bulb is there, which will automatically go up. Okay, that means the bulb is going in, there must be some kind of current that is produced inside the coil, but there is no battery itself. So that means by moving a current, by moving a magnet inside a coil, I can generate electricity. Okay, so this is the first experiment carried out by Faraday. So Faraday was the first scientist who discovered this technique that whenever I move this magnet, that means I am producing something which will introduce the effect of current. So that means the reverse is also true. That means if I am going to produce the I now produces B. So this is the first topic. Now the second topic is that B can produce also I. Answer is yes. It can produce. Okay. That means now we can produce electricity current. Initially, once we are supplying the current, that means there is a battery. So from this battery, the current is going to. Now in the second situation, what I am answering that now the B can produce the electric current. So there is no need of battery in this. The bulb is glowing without any battery. Okay. So this will confirm that some amount of current has to flow. Okay. So it is also observed that whenever I move the magnet towards the coil, the bulb will glow. And if I move away from it, then the bulb will not glow. Okay. So whenever I am moving inside, then the bulb is glowing. And whenever I am moving outward, that means bulb will switch off. Okay. So it will not continuously glowing. It glows and then go back. Then again goes like this, so it will change it. Okay, so this is the first kind of observation that we make from this area. Okay, so electrical energy is converted to the mechanical. In all the experiments, if I supply, so let us say there is a drill. So when you supply this current, something is there, which is there, that is basically the DC motor. So inside that there is a DC motor, so which will produce the mechanical energy. Okay, so now the electrical energy I am giving as the input, and that has been converted into mechanical energy through this DC motor, and because of this drill bit will rotate. Okay, similarly electric fan. Once you supply the electric current to this fan, then you see the fan is rotating. That means you are supplying electrical energy and I am getting the mechanical energy. Okay, like the pump. Also the pump shaft will rotate when we supply the electrical energy. In all of this setup, input is our electrical energy, and finally I am going to convert the mechanical. Okay. So whenever electrical energy is converted into mechanical energy, then the working principle is from electrical energy means I am getting the I. So from I am getting the B, and from B I am getting some kind of force which is basically used to produce the torque or the turning effect. Because of the turning effect only, the fan will rotate or the drill bit will rotate or the pump will rotate. Every time I am giving the rotational form of energy. So the mechanical energy is nothing but the rotational energy that I am getting by rotating some kind of device, rotational energy. And this is well established. That means whenever I am supplying the current, I am getting the kind of energy that is called the mechanical energy outside. Okay. Now, so electrical energy is converted to the mechanical energy in all of the devices. That means whenever I am supplying the electrical energy, that means I should need a battery. Now that conversion of the electrical energy to the mechanical energy is done by a particular device which is known as the DC motor. Okay. So DC motor is a device which is basically convert the electrical energy to the mechanical energy. From the name it suggests that whenever you supply the current, so there is a battery, there must be one battery which will supply the current in this direction, and because of that there is the rotational motion of this device. Okay, so this rotational part is known as the armature. This is the armature. So that is basically the coil part. So I have to rotate this coil by supplying the current. So what I am doing basically, I am giving the current and it will produce the magnetic field. Because of magnetic field, magnetic force will come into the picture, and because of magnetic force, the rotational effect, the torque will develop. Okay, torque for turning. Because of entire process, the coil will rotate. Okay. So now the question is that reverse is also true. How mechanical work is converted to electrical? Now I am going to go from the reverse process. So that answer is nothing but our chapter. In this chapter, we are looking for this particular thing that now as an input, I am going to supply the mechanical. And as an output, I am going to get the electrical power energy. So whenever I am going to get mechanical energy, whenever I am going to convert mechanical to electrical, that means we go for a device known as the AC generator. Okay. So that is the basic device which are going to introduce in our topic, later part of the topic basically. So initially what we are trying to understand that how this conversion is possible, why this conversion is possible, what happens exactly. Okay. So in this first process, we know that how this conversion takes place. So initially the current is there, so that produces the magnetic field, that produces the force, and ultimately that produces the turning effect. And because of that turning effect, that means I am getting the mechanical energy as the output. And as an input, since I am getting the electrical energy, so I am getting the current as an input. So this is the well-known conversion. But now I am looking for the second conversion. The second conversion is that I want to answer the question that how mechanical energy is being converted to the electrical energy. That means in this particular setup, there is no battery. In this animation, there is no battery. But still, I am getting some kind of electric energy. How to ensure that whether I am getting electric energy or not? For that, there is a setup that is, let us say, this is ammeter. So ammeter coil is showing the deflection. Ammeter coil is showing the deflection. That means I am getting some kind of electric energy. How? By rotation of this coil. So once I rotate this coil, that means I am getting the mechanical energy as an input, and correspondingly I am getting the electrical energy as an output. But this electrical energy clearly shows that it is a kind of energy which is oscillating. So if I see this is the ammeter reading, initially let us say it is marked at 0. For some instant it rotates in the clockwise direction, and for some other instant it will rotate in the anti-clockwise direction. That means the current that I am getting is changing its direction. Okay, changing its direction. That means we are going to introduce current that is known as the AC current. Okay, here I am getting the AC current as our output. So that's why this particular setup is known as the AC generator. I am generating the AC current. So that's why the name of the setup is AC generator. This is nothing but a setup which is used to produce the AC current. Okay, let us say I want to get DC current. Let us say I want to get DC current. So for that I should use a battery. So once I use a battery, that will produce the current, and that is unidirectional. There is no change in the current direction. So if I allow this current to flow through a resistor, it will always flow in this direction. It will never change the direction. That is the current that I am getting out of this battery is basically the DC current. Okay, so that's why it is known as the DC source. Known as the DC source. Okay. Now here in this particular topic, I am looking for the AC generator. That means it is known to be as the AC source. Okay. So this is the symbol of the DC source. The symbol of AC source is like this. So you have to draw a circle and then carve one. So that will give the DC source, AC source symbol. So with that AC source, I am now going to convert the mechanical energy into electrical. That means I want to produce the electricity. Okay. So there are various devices which are useful nowadays with this particular. So with the invention of this particular chapter only, I can generate the turbine. Okay. So there is hydroelectric power plant are there. So in this turbine, what happens? So water is allowed to impinge on this bucket. So once the water will impinge on the bucket, so bucket will rotate in this direction. And because of this rotation, that means I am generating the mechanical energy. Now this mechanical energy is converted with this instrument, that is the AC generator. This is the AC generator. Okay. And ultimately the current is being. So I can ensure that if I connect a bulb, so bulb will glow. So because of this invention, because of this chapter itself only, I can produce the electric current. Okay. So nowadays all our equipments run on electricity. Majority of the equipments are run on electricity. So how to produce that? So this chapter will give you the answer how I am going to produce that. Okay. AC means basically AC current means that direction is always changed. Okay. Direction is always changing. And DC means it is unidirectional. Once I am supplying the battery, once I connect the battery, so there is a positive terminal, there is a negative terminal. So current will always go in this direction. It will never change the direction. But whenever I am using AC, so current will flow. Let us say I am drawing the same circuit, there is a resistance connected with an AC source. Okay, connected with an AC source. So through that resistance, for some period of time, current will flow in this direction, and for some other period of time, current will flow in this direction. That means the polarity of this source is going to be changed. Okay, why? Because in this situation, polarity remains fixed. So one side is positive, it will always remain positive. But here, the positive side is positive for some period of time, and negative side becomes negative for some other period of time. That means now the current can change its direction. Now, whenever there is a direction change, then that current is known as AC current. Okay. Now, later part of the chapter, we will understand why the requirement of AC comes into our life. Initially, all the setups run on this, but why the invention of AC is essential, that also we will learn through this chapter. Okay. So, these are the basic devices. All turbines are working on this particular principle where I am going to convert the mechanical work to the electrical. So, electricity is generated by a generator or a turbine, and that generator is known as the basically our AC generator. Okay. Now come, so far we understand why the requirement is essential, because I want to produce something electric, and we already got the answer that electricity can be obtained by changing the B, changing magnetic field. So magnetic field, whenever I am going to introduce in this particular topic, that means now I am saying that I want to change the magnetic. So once I change the magnetic field, then only I can say that now I can produce the electric current. Okay. So first part of this chapter is basically some kind of experiment. Okay. So what is the experiment? So there is a magnetic field. So these are the symbols of magnetic field. Cross means into the plane of it. Cross symbols are into the plane of it. Into the plane. Means magnetic field is a vector quantity. Let us say I draw a piece of paper, and if I say that the vectors are going inside this plane like this, that means it is a cross magnet. Okay. If the magnetic field lines are coming out of the paper like this way, then it will be like what magnetic field. Okay. So let us say I do the experiment that I introduce a magnetic field, and that magnetic field, let us say cross magnetic field, that going into the plane of paper. And if I allow the magnetic field to change with time, if I allow the magnetic field to change with time, once I place a loop inside that. So this is a loop. Okay. I place a loop in a magnetic field, and I gradually change the magnetic. Magnetic field is gradually changing with time. Magnetic field may increase or may decrease. And what you observe that when we change this magnetic field, if I increase the magnetic field or we decrease the magnetic field, then what happens? Then we observe that some amount of current will flow through this. Okay, some amount of current will flow. In the second situation, what you do? So I change the area. Now, by changing this radius, I can change the area of the circle loop. Okay. If I increase the radius, then the area will increase. If I decrease the radius, then the area will decrease. So what you observe that by increasing the area or decreasing the area with time, again with time, again you observe the current will flow. Okay, I will flow. Once you rotate this and the direction of rotation is into the plane of theta. Okay, I rotate this in this direction. So what you observe that no current will flow. Here I is 0. No current will flow. But once you rotate in a vertical axis like this way, then you observe that there is a current. So here in this fourth figure, you observe that I is not equal to 0. I will flow. Okay. So these are the basic experimental observations that we perform initially by placing a loop inside a magnetic, and that magnetic field known as external magnetic. That magnetic field can be produced by the permanent magnet or can be produced by the electromagnet. Okay. So whenever I am producing the magnetic field and under the magnetic field I am placing a one loop and I am observing how the loop is behaving, how the loop is behaving, whether the current will flow or not. How to ensure whether the current is flowing or not. So for that you have to use the help of one instrument. So if I place an ammeter connected with the loop, then the ammeter deflection will be given. Okay, so ammeter will deflect and that means I can ensure that some amount of current is being flowed. Okay, so only in this situation there is no deflection of ammeter. So ammeter reading will be 0. There is no reading. No reading means I can ensure that there is no current is being flowing through that third situation. Only current is being flowing from the first one, second one, and the fourth one. And this will conclude that why the current is being flowing. Now the answer is clear to us that either by changing the magnetic field, or by changing the area, or by changing what? Changing angle. Here I am changing the angle. What? Angle within the B and area. Okay. So area is a vector quantity. Similar to the B is a magnetic field, that is a vector quantity. Area is also a vector. Okay. So how to check what is our area vector? So for area vector, I have to consider that if the B vector changes, then current flow. If A vector changes, then also current flow. If theta changes, theta is what? Theta is the angle between the B vector and I vector, then current will also flow. So these are the experimental observations. Okay. Now summary of this is that by changing these three quantities, what I am going to change? A new quantity known as the magnetic flux. This is represented by the phi. So phi is one quantity, we define it as a flux quantity. So basically, whenever the flux changes, the current will. Now the question comes, what is flux? The flux is a physical quantity, phi, which is equals to dA times cos theta. Okay, magnetic field into area into cos of theta. What is theta? Theta is the angle between the B vector and A vector. So first of all, I have to understand what is phi. So phi is a physical quantity which can be measured by this formula, that is B times A into cos theta. Okay. Now what is phi? Phi is the flow. Flow of what? Flow of magnetic field. Let us say there is a tap. Okay, let us say there is a tap. So from that tap, let us say the water is coming. Okay, water is coming in. So if I put a glass below it, so then the glass will be filled. The glass will be filled. Now, how much amount of water is pouring inside the glass, that will determine what is the flow rate of water. Flow rate. If I open the tap very slowly, then the flow rate will be less. If I open the tap at a faster way, then the flow rate will be more. So this flow rate defines what? Flow rate defines the flux. Okay. The flow of anything is nothing but the flux. So flow of water, here is the flux. So if I hold the glass in this way, then the glass will be filled at a fast way. So if I, let us say the same tap is there, but I am placing our glass in this manner, then the amount of water that goes inside this will be less. Okay. So that means the flux will be less. Flux will be conversely. So flux means what? Flux means flow. The flow of what? Flow of not only water, because here I am using the analogy of water, but here I am not filling the glass with the water. Actually, what I am doing, I am filling with some kind of magnetic field. Okay. So flow of magnetic field line, basically there is a called the flux. That means if there is any change in the flux in the loop, then there is a current in it. That is the final observation. So that means Either by changing B or by changing area or by changing theta, I can get the flux. Okay, I can get the flux value. So we are not sure. If I change the flux number, then only the magnetic field will be there. Yeah, then only the current will be also there. Okay. Now regarding the flux. The flux is what? Definition of flux is that flux is the measurement. Flux is the measurement of flow of magnetic field through an area. So flow is the keyword. How much amount of magnetic field line crosses a particular area? If I count that particular number, that number will define the flux. Let us say there is a coil. Let us say there is a coil. And through this coil, I am supplying some kind of current. So whenever I am supplying current, so magnetic field is being produced. Okay, because I can produce the magnetic field. So once the magnetic field is being produced, and let us say there is an area placed near to the coil. So I can count how many number of lines are crossing this area. Let us say 3 number of lines crossing the area. So that 3 signifies the amount of flux. So I have to count how many number of lines that are crossing the area. So that will give the amount of flux. So flux is the measurement of flow of what? Flow of magnetic field. So that I want to calculate. Now regarding the area, this is the number of magnetic field. So I want to calculate how many number of magnetic field lines crossing the area given. So whenever there is an area, so this is basically a circle. Let us say this is a circle which is making an angle with some kind of the B area. So if you draw a perpendicular to this, if I draw a perpendicular line to this surface, so that will define the area. So this area vector is what? Area vector is perpendicular to the surface. Okay. So this area vector should always be perpendicular to the surface. Then only I can say that will be the direction vector. Let us say I am taking this is the circle. This is the circle. Okay. So direction of the area vector may be either vertically upward, this is the area vector direction, or downward. If I take upward as positive, then downward should be taken to as negative. Okay. Both the way I can take it either upward or downward, but it should always be perpendicular to the surface. Perpendicular to the surface. So once I insert this A vector, let us say this is A vector, now I can comment that theta is the angle between the B vector, so B and the B vector. Okay. So corresponding to that, what I can say, the flux. So magnetic flux is written by the symbol phi suffix D. Phi suffix D. B stands for the magnetic. So phi B is nothing but B times A into cos theta. That I can use it. So depending on the value of theta, cos theta, the flux is a scalar quantity. That number can be positive, that number can be negative, or it can be zero also. Okay. So it is a scalar quantity. That means it has no direction sense. Only thing the magnitude part is there. I can calculate the magnitude by calculating dA into cos theta. This product. So unit is Tesla into meter square. What is the Tesla? Tesla is the unit for magnetic. Tesla is the unit for the magnetic. So that is the area B into A, and cos theta is no unit. So Tesla into meter square, also known as the Weber. Weber is the unit of flux, and Tesla is the unit for magnetic field. So 1 Weber is nothing but 1 Tesla into meters. So there is another CGS unit, which is known as the Maxwell. 1 Maxwell equals 10 to the minus 8. Okay. So most popular unit for the measurement of flux is the Weber. We often use Weber unit to measure the flux, and flux is a scalar quantity. And for a constant magnetic field, constant magnetic field means when the B is constant. Constant magnetic field B, I can define the phi B as dA into cos. This is the answer for this phi B. Okay. And unit is either I can go for Weber unit or Maxwell. Both are available to us, but we mostly prefer the Weber unit as it is measured in SI system. Okay. So calculate the flux of magnetic field to this area. Let us say this is the B and this is the area vector. Okay, area you have to draw always perpendicular to the surface. So this is the area direction, 90 degree. So for this particular situation, I can say clearly that the theta angle is 0 degree. Theta angle is 0 degree because both are parallel to each other. That is theta is 0. So cos theta cos 0 is 1. The answer is BA. So phi should be equals to BA cos 0. BA cos 0 degree. So ultimately answer will be BA. Okay, BA Weber. If I calculate in SI unit, so BA time will be the answer, and that should be Weber unit. Okay. Now if I bend this, let us say now the angle becomes 60 degree. Area is directed at an angle 60 degree to the magnetic field line. So now it becomes phi should be equal to BA cos 60, and cos 60 is half. So BA by 2. BA by 2. So if I place the loop, so if I place, so this is our area. If the area is placed parallel to the magnetic field direction, theta 0. Theta 0 means now the area vector is parallel to our B vector. And in that situation, I am getting the value as BA, and that is the maximum value of x. Okay, the maximum value of x. Because cos theta maximum value is 1. Okay, so I am getting the maximum value of x. And when I incline this area, I am inclining this area at an angle 60 degree. Now I am getting low amount of some amount low value, half of that value. Okay, I am not getting the same value, but the BA by 2 I am getting. Okay, further integration. Now let us say the area is directed in the other direction and magnetic field is even in the same direction. So B is in this direction. So now the angle becomes this angle. So this is our theta angle. Now theta becomes 120 degree. Okay. Now cos of 120 degree is minus. Cos of 120 is minus 1. So here the answer is flux should be equal to minus BA. So it should be negative number. So flux is a scalar quantity that can be positive, that can be negative, that can be zero. Now, whenever B is parallel to A, flux is the maximum. Who is the maximum? Whenever B and A are anti-parallel, now here B is not parallel, B is parallel to minus. Why minus A? Because if I draw A on the left hand side, so positive A is on the left hand side, so negative A should be on the right hand side. B vector minus A vector parallel, or I can say B vector is anti-parallel to A. So this is a symbol of anti-parallel. Anti-parallel. So whenever these two vectors are anti-parallel to each other, that means in this situation theta becomes 180. Theta becomes 180. And cos of 180 is basically minus. So answer of this situation is minus B. So this is the minimum value of flux that I am getting. Okay, minimum value. And this is the maximum. So between BA to minus BA, all the value of flux will. I cannot get any value of flux which is more than BA number, or I can get any value of flux which is less than minus BA. That is also not possible. So these are the extreme conditions. Either I can get plus BA or I can get minus. Now the third situation is that if the B vector and A vector are perpendicular, so in that situation theta becomes 90 degree. So pi B becomes 0. So there is zero flux. Zero flux. So zero flux means no amount of magnetic field lines are crossing the surface. All the field lines are passing on the surface like this. All the field lines are passing through the surface like this. They are not crossing. They are touching. Okay. Touching and crossing are two different words. They are touching. Okay. So that means I can conclude that there is no flux. So flux is zero. Flux may be positive. Flux may be negative. All depends on the angle. Okay. All depends angle. So now we know that how to calculate the flux. Now the chapter is divided into two basic. Our observation is two basic observation. What is experimentally found that whenever there is a change in flux, whenever phi changes, there is a change in phi, then it will produce some kind of flux. Okay, this is the experimental observation. Now divide this chapter into two different segments. First segment is to calculate the direction of current, in which direction the current is. Okay. And second statement is what is the magnitude of this current. Okay. So there are two basic laws that will define the direction of current and the magnitude. So direction is defined by the Lenz's law. So direction is defined by the Lenz's law, and magnitude of current is defined by the Faraday. Okay. Now, so these are the two basic objectives of our study. So we know that whenever there is a phi changes, there is a I. So now what is the amount of current that we discuss in the second part? So first we understand what is the direction. What is the direction of current? That on the Lenz. So now we discuss about the Lenz. Okay. So Lenz law means, so you understand that the current is being there. Okay. So the basic statement of Lenz law is that I hate change. I hate. So who is hating the change? Basically the loop on which our main focus. Okay. So try to understand very carefully that this is our loop. This is our loop. Okay, and this is the symbol of galvanometer. This is the galvanometer. What galvanometer measures? Galvanometer can measure the very small amount of current. Okay, it's similar to that. Okay, so this loop is saying that I hate change. I do not accept any kind of change. Okay, change of what? Change of flux. Okay, let us say there is a magnet. So before that, you should know that if I say this is a permanent magnet, north pole is there, south pole is there. For the permanent magnet, magnetic field lines are coming from the north pole. Okay, and they are going towards south pole. They are going towards south pole. Okay. Now there is a permanent magnet, and I am bringing this magnet towards the north, not towards the loop itself. Let us say this is the north pole of the bar magnet. I am moving the north pole towards the loop itself. So according to the loop is saying that I hate change, means that whenever I am moving the permanent magnet towards the loop, so the magnetic field that coming from the north pole, the black color magnetic field are crossing more. Okay, this black color magnetic field line will increase. Why? Because I am moving the magnet, permanent magnet towards the loop. So this black color magnetic field line, those field lines are coming from the north pole are going to increase. So as the loop is not accepting this. Why? Because loop tries to say that loop is saying that I hate him because I don't want that increase in B will affect myself. So for that, loop will try to produce a opposing effect. Okay, opposing effect. What is the cause? In this cause is the increase in B, black color B. This is the increase in B, that is the cause. Now as a loop will try that he will produce another magnetic field in the opposite direction, so that the effect of this increase in B can be eliminated. So the loop will try to produce a magnetic field in this direction. The red colored magnetic field is produced by the loop, and that's why this is known as the induced magnet. Okay, so I am moving the parallel magnet toward the loop. So what the loop sense? Loop sensing that the black magnetic field will increase. Okay, but loop will not accept this change. Loop tries to oppose this change. So how to oppose it? So it will produce another type of magnetic field in the opposite direction. Okay, so that means the loop is producing magnetic field. Now how the magnetic field can be produced by the loop? I know that. That means loop is going to produce some kind of current. Loop is going to produce some kind of current. Unless and until the current is going to the loop cannot produce the magnetic field. Loop is producing the magnetic field in the opposite direction, means there must be some current being produced. Now, what is the direction? How to sense the direction? So, for that, you have to place your thumb towards right. Okay. Why? Because the induced magnetic field is towards right. So, place your right hand towards right and curl the finger. Once you curl your finger from this side, as an observer over here, let's say the observer is there. So from the left hand side observer, if you see that, so you place your thumb on the right hand side, and if you curl your finger, so finger will curl in this direction. So that direction from the left hand side will be in the clockwise direction. It is my point. Okay. So that is the direction of the current. So in clockwise direction, the loop will allow the current to flow. Okay, so you can clearly see that whenever I am moving the north pole towards the magnet, the deflection of the galvanometer towards the clockwise direction. You can observe that the galvanometer will be deflected in this direction. Right? So whenever you are moving the magnet towards the loop, there is a clockwise current, and because of that, the galvanometer will deflect in the clockwise direction. Now, whenever moving out, the second situation now, let us say now you are moving this magnet in the opposite direction. So in this direction. So that means the magnetic field that is coming from the north pole, this magnetic field line for the loop is going to decrease. Now, whenever you are moving away the magnet, then the magnetic field line, that the black color magnetic field line is going to decrease. Again, the loop hate this change. And according to the loop, if you see, the loop is sensing that for that particular loop, the black magnetic field line is going to reduce. So that means now the loop will produce the magnetic field line, which is the induced magnetic field line, will be in the same direction as that of the black. Okay. Why? Because it is reducing. So in order to change that opposite effect, you have to increase in the same direction. So now the magnetic field line is towards the loop. Okay. In the second situation, if I draw this figure, so that means now the induced magnetic field line is toward this. Yeah. So place your right hand according to that direction and you curl the finger. So now the curling will be in this direction. Okay. If you place your right hand toward the left hand direction, left hand side, and if you curl the finger, then the finger curling will be in the clockwise, anti-clockwise direction as seen by the observer. So for the observer who is placed on the left hand side, he sees that the current is going in the anti-clockwise direction. That means the direction of the galvanometer should be in the opposite direction. You can clearly see that whenever the magnet is moving away from the loop, now the galvanometer is deflected in the opposite direction. That means the current is changing its direction. In some situation, the current is moving the clockwise. In some other time frame, the current is moving in the anti-clockwise direction. That means this type of current can change its direction. That means the current that I am going to get out of this loop is nothing but the AC current. Okay. So this is the basics of the Lenz's law. So Lenz's law statement is that I create change. So what is the change? Change is basically creating by the cause. Who is the cause? Cause is the movement of this magnet. The movement of this paramagnet. Whenever I am moving this magnet, so the magnetic field produced by the paramagnet either increase or decrease. So these are the two options. So both are basically the change that has been imposed on the loop. Okay. So on the loop perspective, loop is seeing that the magnetic is moving towards the loop. That means loop is not accepting. So in the other way, so loop tries to oppose that. So for that oppose effect, so it will produce an induced magnetic, and that will later known as the induced EMF, electromagnetic force, or induced current. Okay, all are basically induced effect. All are induced. Why induced? Because it is being induced by the movement of the magnet. Initially, it was not there. Once I start to move the current magnet, then only this effect will come, and that's why it is known the induced effect. Induced is nothing but influenced by some other. So magnet is there, current magnet is there. So that will influence the loop to produce the other type of magnetic field. So the magnetic field produced by the loop is known the induced magnetic field. The current produced by the magnetic loop is known the induced current. All are basically induced. Okay. So induced EMF or EMF current opposes the causes by which it is produced. That is the first statement. And once you discuss the Faraday's law, then you see that Faraday's law gives the explanation of this Lenz's law. So forget about this expression, it is a differential operator known as. So if I want to write it in a simpler way, so epsilon is a symbol for the induced EMF. Okay. So induced EMF produced by the loop is nothing but minus of delta phi by delta. What is delta phi? Delta phi is the change in magnetic flux. And delta phi by delta is the rate of change of magnet. Why? Because whenever I am moving this magnet, so it will take some amount of time to produce the delta phi effect. So as I am moving slowly towards the loop, so what I am observing that the flux to this loop is increasing, right? Because the black magnetic field is increasing, that the flux is increasing. Okay, that means the rate of change of flux is. So by what time the flux is increasing? Let us say once you start a movement, let us say starting from 0 to 2 seconds, 0 to 2 second flux increases. Okay, again say let us say 2 to 4 second flux decreases. So between 0 to 2 second flux is increasing, that means there is a rate of change of flux. And between 3 to 4 the flux is decreasing, that means we are moving away the magnet. Okay, moving away the current magnet. So that means now the flux is decreasing. That means in both of these two situations, there is a rate of change of flux. And if I want to measure the rate of change of flux, that will give the answer of induced EMF. That is the basic of the Faraday's law. Now, in the Faraday's law, there is a negative sign. The negative sign means that opposite. Okay. So, analytic wise, so if I want to calculate the epsilon induced, that should be simply delta phi by delta t. But once we write the negative sign inside that, that will give the idea that there is an opposing effect. Why the opposing effect is there? Because loop is not accepting the change. Okay. A direction of induced current. How to ensure that what is the direction of induced current? I have already said that the flux may increase or may decrease. Okay, whenever I am moving this current magnet towards the our loop. So this is our loop. So whenever I am moving the magnet towards the loop, so this magnetic field line, the blue color magnetic field line is going to increase. Okay. Yes. So that means the flux is increasing, or I can say the flux is increasing. Okay. Because this area through the flux is cutting. So this is the area cross section. Okay, that remains same. Through this area, red color area, the blue color field lines is increasing. That means the flux is increasing. So increasing flux is the cause. Now the loop will try to reduce this flux. So in order to reduce the flux, so there is another magnetic field that is produced in this direction being. Okay. So whenever I produce an induced magnetic field, that induced magnetic field should be in such a direction so that it will try to oppose the increase in flux. Okay. So magnetic field due to induced current will be opposite to the existing magnetic. Existing magnetic field is towards left, opposing effect should be towards right. So because of that, the current will flow as a observer on the left hand side, who is placed on the left hand side. Now the observer will see in the clockwise direction current. Okay, you will see the clockwise direction of current. Now similarly, if I move away the magnetic, now I am moving away the magnetic current magnet. That means for the loop, this flux is decreasing. This flux is decreasing. So in order to produce the opposing effect, now the loop will try to produce the induced flux or induced magnetic field in the same direction, so that the opposing effect will be nullified. Okay. So one parameter is decreasing in the left hand direction. If I increase that parameter in the same direction, then the effect will be nullified. Okay. So now the magnetic field is produced in the left hand direction. As an observer who is placing himself on the left hand side, for that observer, he will see that the current will now flow in the anti-clockwise direction. So this is the second case. So these are the two possible situations. Either the flux may increase or the flux may decrease. Okay. So depending on that, the direction of magnetic field will change. So if the flux is decreasing, so let us say there is a loop. There is a loop. So I am moving this magnet towards our right side, towards the right hand side. So corresponding to this, what we can observe that these magnetic field line coming from the north pole is decreasing. Red color magnetic field line. Okay. So that not nullify the effect, I have to produce the magnetic field in this direction, B induced. That means for the loop, left hand side is the B induced direction. So if I rotate my thumb, rotate my curl the finger, so finger will be curled in the anti-clockwise direction. So the galvanometer show in the anti-clockwise direction. Okay. The same logic, if I move this towards the loop, now the red colored magnet will increase. This red magnetic field line will increase because more number of magnetic field lines try to cross the loop. So B will increase. As a result of which, now the induced magnetic field will be in the opposite direction, in this direction. B induced. So now the deflection of the current should be in the clockwise direction. Okay. So either the current may flow in the clockwise or it may flow anti-clockwise. It depends on in which direction I am moving the magnet. Okay. So the magnet can be moved. Or keeping the magnet to fixed, I can move the loop also. Both of the same effect. Na? Instead of moving the magnet away from the loop, if I move away the loop from the magnet, that is also same. And that will be also the same effect. Okay, similarly, either I can fix the loop. Here the condition is that I am fixing the loop and I am moving the magnet. Or in some situation, I can fix the magnet also and I can move the loop also. Both are acceptable. Both are possible. Only thing is that I have to produce some kind of change. Okay. Let us say there is a fixed magnet. So here now I am not moving the magnet. So these magnets are fixed. The fixed magnet. They are not moving. So what I am moving? I am moving the loop inside and outside. Whenever I am moving the loop inside, whenever the loop is moving inside, so more amount of area is intersecting with the magnetic field line. Can I say that? Because whenever the magnet is fixed, so inside that the magnetic field lines are fixed. This is the B direction. Okay. Whenever I am moving inside the magnetic field region, that means through that particular loop, in this direction, the B will increase, or rather I can say the flux will increase. Okay. So as the B increases, as I am moving inside the magnetic field region, so gradually our field will increase, that means flux will increase. In which direction? And the black direction. Okay. So as a loop will try to produce the induced effect in the opposite direction. So if I want to produce an induced effect in this direction, so taking the thumb in that particular direction, if I rotate my finger along the loop, so I can see that for this direction, the thumb or finger should rotate in this direction. Okay. So for an observer who is placing himself on that particular side, he will observe that anti-clockwise current will. Whenever I am moving away this loop, from the magnetic field, and gradually the flux will decrease. Now the flux is decreased. Now the moving away from the magnetic field region, the flux is decreasing. So which flux is decreasing? B is decreasing. So induced effect will be in the same direction. Okay. So whenever moving away, so that means now the induced effect will be in this direction, B induced. Okay. So for this, the magnetic field current should go in the clockwise direction then. Okay. So for the observing that in some portion of time, the current is in the clockwise direction, and in some other situation, the current is flowing in the anti-clockwise direction. Okay. Why? Because the induced magnetic field is changing its direction. Yeah, two different directions are possible, either clockwise or anti-clockwise, and the sign and the direction is very carefully understood that it will always try to oppose the change. Once you identify what is the cause, then you can conclude what is the change, corresponding change. So finally, what you can say that there are four possibilities. There are four possibilities. So right now I am saying that there is cause. What are the cause and corresponding opposing? I am identifying what are the causes possible. So causes may be either the cross magnetic field will increase. Okay. The cross magnetic field may increase, or cross magnetic field may decrease, or dot magnetic field may increase, or dot magnetic field may decrease. So these are the four possible. Now remember that as an opposing effect, I cannot produce any kind of effect which is decreasing. Always the effect should be increasing in nature. Effect can never be decreasing. Increasing cross magnetic field, opposing effect is decreasing cross magnetic field. Okay, but I cannot do that. Why? Because opposing effect, under the opposing effect, decrease in any quantity is not possible. Okay, so in the other way, what I can do, instead of decreasing the cross magnetic field, what I can do, you can increase the dot magnetic field. That will also increase, because reverse of cross is dot. Okay, reverse of cross is dot. So cross is increasing. Cross is increasing into the plane of paper. Some kind of field lines are increasing. Magnetic field lines are increasing. So opposing effect is that you have to produce the magnetic field line in the other direction. That is the dot direction. Okay. Let's do this equation clearly. Let's say this is the plane of paper. I am saying that these magnetic field, yellow magnetic field lines are increasing. That is the cross is increasing. So I cannot decrease this yellow line. What I have to do, I have to produce the magnetic field which is in the opposite direction. In this direction, I have to increase the green line. So this increase green line is nothing but the increase in dot magnetic. Okay. So that's why increasing cross has to be supplemented by increasing dot. If I reduce the cross, then the opposing effect is increasing cross. Okay. If I increase the dot, opposing effect is reduce the dot. Again, that is not possible. If I say this is the dot type of field line, this is a dot type of field line. Coming away from it. If I say these dot field lines, these green colored field lines are increasing. So opposing effect is that you have to produce the magnetic field in the other direction, in this direction. Then we have to increase this cross magnetic field line. Okay. So increase in dot cannot be supplemented by decrease in dot. It is not possible. What you have to do, you have to produce the cross magnetic field to be increased. Okay. Decrease in dot means increase in dot. This is so these are the four possible opposing effects produced by the causes. So whenever there is a cause, the loop has to produce this opposing. So depending on these opposing effect, I can now identify what is the proper direction of the induced current. Let us say B is decreasing. That means dot magnetic field is decreasing. So dot magnetic field is decreasing means you have to produce the effect that is dot magnetic field increase. You have to increase this dot magnetic field in this loop, inside the loop. So you have to place your thumb towards yourself. So towards yourself means dot. Into the laptop screen means cross. When I place my thumb, right hand thumb, towards myself and rotate my finger, if I curl my finger, placing the thumb towards myself, in the direction of curl should be in this direction. Nah. So this is the direction of induced current. That means what you can see that this direction is anti-clockwise direction. So whenever the B decreases, so loop will produce a current in the anti-clockwise direction to nullify the effect of the cause. So this is the cause. This is the cause. And increasing dot inside the loop is the effect. So effect has to be such way so that it will reduce the cause. Similarly, let us say there is a current carrying wire. Through this current carrying wire, the current is being increased. As I have already said that the magnetic field can be produced, external magnetic field can be produced by either a current carrying wire or a loop or a permanent magnet. Okay, anything can produce the magnetic field. Now in this situation, I am using a current carrying wire that will produce the magnetic field. Now what is the direction of the magnetic field for the center? So for that again, you place your thumb along the arrowhead direction, along the direction in the transition point. If you curl your finger about that particular point, you can feel that your finger is going into the plane of it. Placing the right hand thumb along the direction of the arrowhead, if you curl your finger, then you are saying to the self that the finger is going into the plane of paper, that means cross. Understood? So increase in I means this cross magnetic field within the loop will increase. Okay. So that becomes the cause. That becomes the cause within the loop. The loop will not allow this cause to be there. So it will produce the opposing. So increasing cross. So increasing cross means the opposing effect should be decreasing cross. But again, you have to remember that decrease of any quantity is not possible. That is what you can do. I can increase the dot number. Okay. So once I am increasing the dot, so that becomes the opposing. That is the opposing effect, correct opposing effect. Okay. So increasing dot means you place your thumb towards yourself and try to rotate your finger. Once you rotate your finger, right hand finger, so then again finger will show the direction of the current in this direction. Okay. So that is the induced current. That induced current not equal to this current. So this is the real cause. This is the cause. Basically, because of that, this is the cause inside the loop, and that will produce the effect. The effect is called the induced. Okay. That effect is direction of current. So this is basically the Lenz's law. So we are doing the exercise on the Lenz's law. So Lenz's law suggests that whenever there is a cause, there must be some kind of opposite. You have to identify the direction of the opposite. Okay. Let us say there is another loop is there and placed by side A. There is a current carrying wire. Now place the thumb along the current carrying wire. So if I allow the thumb to be there and if you hold my finger, then the finger is basically trying to move out of the plane. Now, if you hold your finger along placing the thumb along the I direction, if you rotate it, so now the thumb will be or finger will be out of the plane. So out of the plane means where the magnetic field will drop. Now this current is decreasing, so this is also decreasing. So this is the cause. The cause is increasing dot. So opposite to that should be the increase in dot. So again the effect will be increase in dot number, and that is a possible. Increase of any number cause of dot is possible. Increase in dot means again you place your thumb towards your skull and curl your finger. So direction of current is again anti-clockwise. So this is the I induced direction. Okay. Now situation is now changed. Let us say again the larger loop is there. Through that the current is being increased. Through that the current is increased. Now whenever the loop is there, now so far what we discussed the where. Now for the where, what you do basically you place the thumb along the current and you curl the finger. Placing the thumb along the, so here also the wire is there. I place my right hand thumb along the arrowhead direction. What is the arrowhead? Arrowhead is the direction in the current is going, and I curl my fingers. Now, whenever the loop comes in the picture, so this is the loop. So for that, the convention has to be changed. Now, in that situation, what you should do, you should curl the finger along the eye. You curl your finger along the eye, and thumb will give the so yes, you have to ensure that your finger is in the vertical. Let us say this figure is in a vertical plane, that is on your laptop screen, and based on this concept, now you curl your finger. So placing your placing your hand, right hand in front of you, and curl your finger. Curl your finger along the arrowhead direction. So once you, that means you are curling along the anti-clockwise direction. So your thumb will be pointed towards yourself. Your thumb will be pointed towards yourself. The thumb direction will be the direction of the magnet. Okay. So thumb is pointed towards myself means dot. So that means here the magnetic field is dot. So increase in I means dot will now increase. Nah? So that is the cause. I identify what is the cause. Now come to the loop. Come to this loop. So for this loop, inside this loop, this orange color loop is feeling that the inside my loop, in my area, the dot magnetic is going to be. So now the reverse effect is that you should reduce this dot, but that is not possible. So what you can do, you can increase the cross magnetic field line. Okay. So this is the induced effect. So increasing cross means you place your thumb along the cross direction. Why? Because that is the induced effect. So you have to place your thumb along the cross direction, that is into the pen of paper, and curl the finger. Rotate your fingers. So rotation should be in the clockwise. Nah. So that will give the direction of the induced current. Okay. Understood. So the concept will be different, logic will be different for the loop. So for the loop, you have to curl your finger along this eye. Curl the finger. Curl fingers along eye. Along eye. Once you curl your finger along eye, then direction thumb will give the magnetic. Direction thumb will give the magnetic field. But whenever I am doing the same exercise in the where, then I have to place the thumb. The thumb you place along the current and curl the finger. Then the curling finger will give the direction magnetic. Here the thumb will give the magnetic field. Okay. So that is acceptable for the loop, not for any other. Okay. Let us say again, coming to the loop. Again through the blue loop, the current is being increased. Current is being increased. So from this point, let us say corresponding to this point, if I say the current is in this direction, current is in this. So take a thumb along this upward direction. You curl the finger for the orange color loop. Can you get the feeling that now the thumb is pointed toward the loop, toward the plane of paper? That means into the plane of paper, that means cross. Corresponding to small current element. For this high current element, I can see that the orange color, inside the orange color, the magnetic field line is going to increase. So this is our cause effect. Okay. So that has to be nullified. That means I have to reduce that effect. To reduce that effect means I have to decrease the cross, but I cannot decrease it. So what I can do as an opposite effect, I can increase the dot. So dot increase is the opposite. In the opposing effect, I identified that. So once I identified that the increase of dot is the opposing effect, that means that you have to place your thumb towards yourself. You have to place your thumb towards yourself and rotate the finger. So once you curl the finger, then the current will be in the anti-clockwise direction. That is the induced current. Okay. So every time in all the exercise, what I have seen that there is one particular current carrying element or magnet is there that is influencing the other. Nah. So one is influencing the other one. So the loop which is influenced by the other one. The loop, this orange color loop is influenced by the blue color loop. So that loop is known as the secondary coil. Okay, this is the name of secondary coil. And the loop who is influencing the secondary is known as the primary. This is the primary. Okay. So every time there is a primary and there is a secondary. So primary is one through which the current is being flowing. That means if I say that through the primary coil the current is being flowing, and in order to supply this current through the primary, I must have to connect with the battery. Huh? There must be one battery. So this battery will supply the current to the primary coil. So primary coil is always connected to the battery. Why? Because inside the primary coil, the current has to be. But because of this primary current, what I am getting the induced current in the secondary coil. So since I am getting this current as an output, that means this current is produced with no battery. Okay. For the secondary coil, no battery is. Okay. So that means this will define which one is primary and which one is secondary. So by seeing the loop, you can identify which one is the primary coil and which one is behaving as a secondary coil. Why? Because for the primary coil, every time the battery or the source has to be connected. Okay, source has to be connected. For the secondary coil, there is no source. So if I replace this battery by a AC source, then I can expect that induced current is also AC. Okay. So that is the idea of the transformer. So in transformer, I am doing the same exercise. Okay. So I am replacing this battery of the primary coil by the AC source. Once I replace the battery of the primary coil by AC source, that means in this particular primary circuit, current is changing its direction. Either current is flowing in the clockwise or it flows in the anti-clockwise. For some period of time, it flows in the clockwise direction, and for some other period of time, it flows in the anti-clockwise direction. Okay. So that means since the primary current can alter its direction, I can ensure that the secondary current that I am getting can also alter its direction. So that's why I can ensure that here I am getting the AC current. Okay, that is the idea of the transformer. Okay, now let us say there is a large coil. So you know that this is a primary coil. Why primary? Because the current is going in the primary coil. So this is a loop. For the upper part of the loop, if you allow your thumb to place in this direction, you place your thumb along this direction and hold your finger. So fingers are going inside the loop of the orange. If I place my thumb toward left hand side and if I move my finger, then I can feel that the current is being flowing outside the loop, outside the larger loop in the dot direction or in the cross direction, where the magnetic field cross. Okay. So if I reduce this current, then the dot is cross is reducing. So this becomes the cause. This is the cause. Okay. The effect should be the increase in dot, increase in cross. So I want to increase the cross. This is the effect through this orange color loop. So increase in cross means you have to place your thumb into the plane of paper, and into the plane of paper means into the laptop screen. Once you place your thumb into the laptop screen and try to rotate your finger, so finger will curl in the clockwise direction. So that will be the reason I induce. Okay. Now another interesting fact regarding this particular exercise is that if I concentrate on the square loop, so if I rotate my finger along this direction means along the direction of current plane. If I rotate my finger, then the thumb will be pointed outward. Curl your finger inside the loop and in the anti-clockwise direction. So thumb will be pointed outward. Means inside the square loop, magnetic field is dot. Magnetic field dot. Outside, every point outside of this is always cross. Okay, so that means a current carrying element will distribute the magnetic field in two different directions, inside and outside. If inside is dot, outside is always going to be cross. If inside is cross, then outside is always going to be dot. That is true for every current carrying element, whether it is a loop or a plane wire. If I say this is a plane wire, who is the current is in plane? If I move to the right hand part of the wire, so for the right hand part the magnetic field will cross, and for the left hand part the magnetic field will dot. Okay. Every time the current carrying element will distribute the entire region into two different segments, one is cross and another is dot. Okay. That is the beauty of the current carrying element. It will always distribute the magnetic field in two different parts, two different regions. If one part is cross, then other part is bound to be dot. Now do the same exercise by moving the magnet. So far I am using the concept of current carrying element. Now I am moving the magnet. So if this is the loop, and that loop is fixed. That loop is fixed. I am not moving this loop. So I am moving the magnet with a certain velocity v. So for this magnet, these are the magnetic field lines coming from the North Pole. As I am moving the magnet for this observer, so that observer is observing that through this loop, this type of magnetic field line is increased. Now, as I am moving the magnet, so yellow colored magnetic field line through this loop is going to increase. So opposite of that will be the induced effect. So induced effect is induced reaction with the being induced. Okay. So in order to produce the induced effect towards left hand direction, that means our current should be in the anti-clockwise direction as per the observer. So observer will see the current will flow in this direction. That is in the towards the left hand direction, it can produce the induced effect. Okay. Similarly, if I move away the magnet, now the south pole is facing the loop. So again the loop is fixed. The south pole is facing. So for the south pole, these are the magnetic field lines that are coming inside the south pole. Okay. And for this observer, this type of magnetic field lines is decreasing. This type of magnetic field line is decreasing. So opposing effect should produce in such a way so that it will increase the magnetic field line in this direction. So this is the induced effect. So that means in order to produce the induced effect towards right, so I have to, for the observer perspective, so observer will see the current should be in the clockwise direction. Okay, he will see the current in the clockwise direction. So depending on the location of the observer, whenever there is a circular loop, if I place the same observer on the side, if the observer is placed on the right hand side of the loop, then for that observer, if this observer is seeing the clockwise current, that observer will see the anti-clockwise. Okay. So that means every time the direction inside the loop, if you ask the direction of the current to be measured from a loop part, you have to ensure that from which direction you are observing that. If nothing is stated in the question, then every time you have to check that direction is towards the left side. No, observer is placed on the left hand side. If the observer is placed on the left hand side, on that aspect, on that particular direction, from that direction, what is the direction of that? That you have to give the answer. Okay. Every time you have to check that the observer is placed on the left hand side. Okay. Now let us say we are asked to calculate the moment on acceleration of the bar magnet as it passes through the fixed loop. Let us say there is a loop which is fixed. Let us say there is a fixed loop. Okay. And you allow the bar magnet to fall through this loop. Inside. Okay. And once you drop a particular ball from a certain height, the ball will always fall with an acceleration due to gravity. Okay. Let us say there is an object which you drop. If you drop this object, the object will fall downward with an acceleration equals to g. You know that? But here it will not happen. Why? Because the loop is. That loop is a fixed loop. So once you are moving the, so let us say now the bar magnet is above the loop and tries to go inside. So for the bar magnet, this is the magnetic field line. This is the magnetic field line. As the magnet is approaching the loop, so this magnetic field line inside this loop will increase. So this is the cause. So loop will produce a magnetic field line opposite to that. Loop will produce induced magnetic field line. Okay. This is the induced magnetic field line. So from the loop perspective, loop is producing the magnetic field line which is away from the loop. Okay. So if I say this is the magnetic field line produced by the loop, that is the induced magnetic field line. Okay. So can I replace this entire loop by a permanent magnet? By stating that loop is behaving as a permanent magnet where this is the north pole, this is the south pole. Why? Because from the north pole the magnetic field lines are coming away. Okay. So I approximate that loop to behave as a permanent magnet. So now let us say there is another magnet is there on top of it, where also this is the north pole and south pole. Now these two magnets will certainly repel each other. Why? Because north and north coming towards each other. So since the repelling effect comes inside this, so acceleration will be less than g. So this a number is going to be less than g. It cannot be equal to g. Okay. Whenever there is a loop, so if we move the loop away from the path, then the bar magnet will fall with the same acceleration, that is acceleration. But if the loop is there, then because the electromagnetic induction effect, so this effect we are going to study is the electromagnetic induction. Why? Because this is induced effect. This induced effect. Initially inside the loop there is no current. Once I place some kind of magnetic field, once I change that magnetic field, then the effect will come. Then only the effect will come. That's why it is called the electromagnetic effect. And that electromagnetic effect is only observed whenever there is a change in effects. Every time I am focusing on the magnetic field, but ultimately what is important? Important flux. How the flux is changed. What is the amount of flux? That you have to calculate. Okay. So this is basically the task to calculate the flux to them. So flux is what? We have already said that flux is equal to B into A into cos. This is the expression. Now let us say this is the loop. Let us say this is the loop. And inside loop there is a square region inside is the magnetic field. So whenever you are calculating the flux, that area is nothing but the area inside which the magnetic field is. Inside which B is. So for this loop, only a part of the loop, not the entire loop, is covered with the magnetic field. Only this part is covered, the square part. So area is equals to A square. Okay, area equals to small a square. So for this situation, flux should be how much? B into A square into cos theta. Now what is theta? Now B is, if I say B is cross, so either I can take area as cross or I can take area as cross. That is in our hand. Okay. In this situation, I also take the area vector is cross into the plane of paper. B is into the plane of paper. So both are parallel to each other. That means theta becomes 0 degree. So cos theta becomes 1. Okay. So answer for this problem is B into A square. Not B into pi r square. So every time whenever I am doing the calculation for the flux, so inside that the formula is B into A into cos theta. What is that A? That A is the area inside which the magnetic field is there. Okay. So in this region there is no magnetic field, no B. So that area you don't have to take. Only take that particular area inside which the magnetic field is there. Here only the square part is occupied by the magnetic. Okay. That means the area should be small a square, not the area of the loop. The area of the loop is pi r square. The area of loop is equals to pi r square. I am not going to use that area. Instead of that, I am using the area small a square. Why? Inside the small a square area only, the magnetic field is there. And regarding the direction of the area vector, every time if the B vector is given, so use the concept that along the same direction area vector is there. Okay. If I say both B and A vector aligned along the same direction, that means theta becomes 0 degree. And if theta is 0 degree, that means cos theta becomes 1. So finally what I am getting is pi equals to B times A square. That will be your answer. So for this situation, you have to only consider the area inside which the magnetic field is there, not the entire. Okay. Let us say now the area is this much portion of the area of the loop is occupied by the magnetic field. Okay. So this area is equals to how much? Pi capital R square by 2 only. So flux should be how much? Flux should be equal to B into pi R square by 2. Because here also I am saying the area vector is cross. Why? Because the B vector is cross. That means theta is 0 degree. So align that B area along the same direction as that of the B. Okay, that means every time I am getting theta 0 degree. So for that cos 0 is 1. So I am getting B into pi r square by 2. Okay. So whenever I am calculating the magnetic flux, so you have to take that particular area inside which only the flux is. That is the magnetic field. So consider that particular area and accordingly calculate the magnetic flux. So flux formula is simple, BA into cos theta. Regarding the theta, if the angle of B is given, so B is given as cross, so for that loop you can assume the area is also cross. Okay. In that situation, in this particular situation, I can also assume that I can assume the area is dot. I can assume it. If I say area is dot and B is cross, then the theta becomes 180 degree. Okay. And for this situation, pi should be equals to B into pi r square into cos of 180 minus 1. So answer is minus B into pi r square by 2. Both are correct. Both are correct. But whenever you are reporting this answer, that means you have to mention that you are assuming that area is cross. And whenever you are reporting this answer, you have to assume that you have to mention that the area you have assumed as dot. And depending on that, the answer will be both are correct. Okay, both are correct. Okay. So now let us say there is a loop. Let us say there is a loop ABCD. ABCD is loop. Now whenever it is, so initially the loop is outside the magnet. No part of the loop is entered. So at this situation, can I say flux is 0? Yes, because area is 0. As I want to enter inside this loop, so gradually the area will increase. So when, let us say, the small portion of the loop, some portion of the loop is being entered. Let us say now this portion of the loop is entered. So I have to take this much area. Okay. So gradually, once the loop is going to enter, the area is going to increase. That means I can say that the flux is going to increase. Ultimately, one point will come when the entire loop is fully entered inside. Once the loop is fully entered inside the magnetic field, now the flux becomes constant. Why? Because there is no change. Okay. So once the loop is trying to leave from this, so then also gradually this area is decreasing. Now, once the loop is fully removed from the magnetic field, then the area becomes 0 again. So once the loop is fully removed, then the area becomes 0, then phi becomes 0. So starting from 0 value to 5, it will increase, then it remains constant, and then again it decreases. And again decreases. So initially the phi is 0, flux is 0. Why? Because no part of the loop is inside the magnet. Now once I try to move inside, gradually the area will increase. Area increase means flux will increase. Once it is increased, it will reach the maximum value once it remains inside the loop field. Whenever it goes inside the field line and inside the magnetic field completely, at this situation the flux is not going to change, it is constant. And once I remove this area gradually, after some point of time, once the area is removed, gradually it is coming out of the magnetic field line, so area is decreasing, means area is decreasing means flux is decreasing. Ultimately, when it is completely removed, then the flux becomes 0. So what we can comment that initially for some period of time, let us say starting from this point to this point, the flux increases. This point to this point, let us say flux remains constant. Now, from this point to this point, let us say flux is decreasing. So whenever the flux is increasing, can I say that the increase in magnetic flux is basically in the cross direction, or rather I can say increase in magnetic field in the cross direction. Now, as the loop is entered inside the magnetic field, and gradually the cross magnetic field is going to increase. So that means the opposing effect should be decreasing cross, that is increasing dot. So inside this, the effect cause is increasing cross. For the third part, decreasing cross. So opposing effect for the first part should be equals to the increase in dot value, then dot number increase. So dot increase means the current will be in the clockwise, anti-clockwise direction. Okay. For the second part, for the third part, decreasing cross is the cause. Opposing effect should be increasing cross. So increasing cross means current should be in the clockwise direction. And in between, whenever there is no change in the flux, the current will be equal to 0. Why? Because current has to be there only when there is a change in flux. If there is no change in flux, there is no current. Understood? If there is no change in current, there is no current is no change in flux, that means there is no change, current is there. So some part of the movement where there is no current, for some part there is a current, and for some other part there is also current, but the direction of current in both the part, let us say I didn't find the number that ABCD, let us say from moving from A to B, I am sensing an anti-clockwise current. Once I move from B to C, the current is 0. When I am moving from C to D, again clockwise current. That means that again the current is changing its direction. Okay, again the current is changing its direction. Understood? So this is the basics of the lens law from where we understand how to calculate the direction of induced current.